So let's start recording and welcome. This is our second module, which is basically the second chapter, which is one-dimensional motion. And this is quite a detailed chapter, so I break up the notes into two bits. In the book, it's typically one chapter, and there's a lot in it, but I break it up into two bits for us. And let's see if I can, let's have a look. Got my pen. Yes, okay. So let's go down here. So we're going to talk about displacement versus distance traveled. That's a new mistake. Displacement versus, we're going to talk about displacement, velocity, and acceleration. We're going to talk about instantaneous velocity and instantaneous acceleration. We're going to talk about things like speeding up and slowing down. There's some confusion about speeding up and slowing down. And then we'll start talking about motion graphs. First part, average displacement versus distance traveled. Then we're going to talk about average velocity versus speed, and then average acceleration versus pickup. There are many times when we don't care about what you do in between. We just care about the beginning and the end. Finances, for example. You really care about where you start off financially and where you end financially. What you do in the meantime is irrelevant. You know, maybe you had a good day, maybe you had a bad day. What counts is your end versus your beginning. That shows the change. In mechanics, we might think that that's not really appropriate because what really counts is how hard I have to work to achieve something. And the reason why I care about effort is because I live in a friction-filled world. And so moving from here across the room takes energy. Whereas if I was in space, moving from here across the room wouldn't take anything, if I was moving to begin with. So then we have a question of, do I try and do my physics with the complicated world that I live in, which I understand, I feel, but is very confusing, very complicated? Or do I try and simplify my view of the world and make it only more complicated when I need to? And that's really what the difference between Aristotle and Galileo. Aristotle, 2,000 and odd years ago, basically looked at the world as it was and tried to make up rules to explain what was going on in this complicated, friction-filled world. He went further than that, unfortunately. He went and tried to describe why things were the way they were. And so he ended up with some ideas that just don't stand up to the test of scrutiny, you know. But he was basically the guy who says objects slow down to a stop, you know. And yeah, you roll an apple across the ground, it stops. So it's not that you don't see that kind of thing. He said the Earth cannot be moving. I mean, 2,000 years ago, some people felt the Earth was moving. That the Earth spun in the heavens rather than the heavens spinning around the Earth. A long time ago, that idea came up, and he would say that can't make any sense because we don't feel any motion and all that kind of stuff. He's looking at a very complicated place, and he's saying what he observes, which is fair enough, but then he's going beyond that and saying why and all this kind of stuff. Then along comes, 1,500 years later, along comes Galileo, and Galileo's an amazing person. And he, first of all, has this realization that he needs to take the complexity out of what he sees. And so he gets rid of friction. And how can he live in a friction-filled world and get rid of friction? And I'll go through how he does that. It's really quite impressive. But he is then able to get this more schemized view of the universe where effort does not matter. The energy that it takes you to climb the hill, you get going back down the hill. So when you're at the same level, it's like you did nothing. The energy that you paid, you get back. You know, there's no taxes. It costs you something to go up and it costs you something to come down, which is what happens in a friction-filled world. He was able to do this. And when he did this, the math got simpler. And he then, maybe not him, maybe Newton a bit later, was then able to add in friction and the like when they needed it. So it's a really good way forward. For us as new learners, it's kind of like we've got to keep reminding ourselves that our common everyday experience is in a friction-filled world, and so it's not necessarily a good indication of what the physics should be. So we've got to be a bit careful about that. And the other thing I'd warn you about with this is that you're going to start seeing symbols, and some of them are going to be Greek symbols and all that kind of stuff. And you're going to basically see equations. And if you're anything like me, when I first saw these equations, I'd kind of like look at it and say, oh yeah, I get it. And I would make mistakes because of just simple things, like sometimes I got the equation kind of backwards. So here's a case in point. We're going to define this thing called displacement. And displacement is your final position minus your initial position. It's not how far you move. And it's not your initial position minus your final position. It's specifically the end minus the beginning. It's your final position minus your initial position. And pretty much all the way through physics, we'll find it's always the final minus the initial, because we want to look at a change. And so what we say is displacement of an object is a vector. What's a vector? A vector is something which has magnitude, size, but it also has direction. So a vector is something which has a size in that direction, which is different from a size in that direction, which is different from a size in that direction. It's got a size and a direction, whereas a scalar is just something that's got size. So my mass is a scalar, but my weight, which is the pull of gravity on me, is a vector. It points downwards. I don't have a weight in that direction. Well, I do, but it's a weird number. I have a weight in that direction. The force is downwards. So it's a good idea to be able to distinguish between scalars and vectors. And you can't just go by plus or minus signs. Unfortunately, where we begin with a single line. We imagine a railroad track with things on it, or a road with things on it, and we say we go forward, we go back. And once we've kind of like got the hang of that, then we'll look at two-dimensional stuff, and then we'll look at three-dimensional stuff. So when you first begin, the vector is either a positive number or a negative number, because there's only two directions this vector can point. And so sometimes people get the idea that if you have positives and negatives, it must be a vector. That's not really true. I mean, temperature has positives and negatives, but that's not a vector. You can't say it's 55 degrees in that direction. You can say it's 55 degrees temperature difference in that direction. But that's a vector grade. That's a temperature gradient. That's not a temperature. So don't be fooled by positives and negatives. And always try to decide, is this a vector, is this a scalar? All the way through, keep asking yourself, is this a vector or is this a scalar? So distance traveled is clearly not a vector, because it can be that way, plus that way, plus that way, plus that way, plus that way, as I go backwards and forwards in my daily life on this single track. So that's not a vector, whereas displacement is the final position minus the initial position, and that is a vector. And so we say displacement of an object is a vector. It has magnitude and it has direction. And I say delta x, and I think of delta x as being one symbol. It's not mathematical. It's not delta times x. It's a name for something. Delta x. And delta x means displacement. And frankly, I don't care if that displacement is in the x direction, the y direction, or the z direction. I'm not going to change my symbols just because of that. Delta x means displacement. I can have delta x in the x direction, delta x in the y direction, or delta x in the z direction. I don't care. I'm going to call it delta x. Other people say delta y and delta z. It's just shorthand. So delta x means displacement, and displacement by definition is your final address, your final position, your final coordinate, all different ways of saying the same thing, minus your initial address or your initial position or your initial coordinate. So I am always envisaging a line, and it has 0 somewhere in the middle, and these are all positive addresses, and these are all negative addresses, and I'm imagining I start off here and I end up there. So that's my displacement for that journey. I start off here and I end up there, so that's my displacement for that journey. I start off here and I go past the origin and I go there. That's another displacement, and so on. This is what I'm envisaging in my mind. The distance traveled is a scalar. It's only has magnitude. There's no real direction. You go there and you come back, and you go there and you come back, and it's just like how far you travel. It's the sum of all the motion without regard to the direction being travelled. And so to try and distinguish between these, I want to show you a typical problem. So here we have an object starts at +3 meters. So let's put our 0 here. I'm going to go 1, 2, 3, +3 meters. And then it says it moves 7 meters to the right. So let's have a look. That's 1, 2, 3, 4, 5, 6, 7. So that took me to +10, I think. +10 meters. So let's draw that in. So I draw in that bit is a vector. It's got a certain direction to it. And then it says it then moves to a point located at -12. Oh my word. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is -12. And it goes from this point here and then moves to -12. So my words are giving you instructions, basically. Let's just think about how I can give you instructions. There's 2 examples here. I can turn around and say which direction you go and how far you go. That's one way of giving you an instruction for a change, yeah? The other one was I told you where you went to. So wherever you're at, you can go to there. I didn't tell you. I could have said it then goes 22 meters to the left, rather than saying it then moves to a point located at -12. I could have done the math. And I could have said, oh, it then moves 22 meters to the left because there's 10 there and there's 12 there, making 22. So that's another way of saying the same thing. I could also say, this is the more confusing one, I could also say it moves to the left with a speed of 11 meters per second for 2 seconds. So now I'm telling you the speed and how long. So I'm saying, oh yeah, you move to the left, so you move to the left, 11 meters per second for 2 seconds. So 11 meters in the first and 11 meters in the second gets you to 22. So 3 ways, but only 3 ways. There's not some wacky thing that, those are the 3 ways that we typically play with these information. So practice interpreting, how can I know the different ways I can give you this information. But however I give you the information, you end up with a number line. You end up with a diagram like this. And we're going to compare and contrast the 2 answers. So first of all, it says, what's my displacement? So I say, well, my displacement is equal to my x final minus my x initial. Why do I write that down every time? Because I want it to be so ingrained in my brain that by the time the test comes, I'm not kind of thinking, what was that equation again? So I write down equations every time. Every time I do a homework, I write down the equation. When I have a problem, I write down the equation because it's just reinforcing what I need to know. And then I say, okay, well, my displacement is equal to, I look at my diagram. This is my start. I like to label the start with an S, and I like to label the end or the finish with an E or an F. And I say, well, what's my final location, displacement, address, whatever you want to call it? It's going to be -12. I put that in parentheses because it's a thing. There's a difference between that negative sign and that negative sign. The negative sign in the parentheses is a direction. The negative sign after the parentheses is an operator. It's subtraction. This first negative sign does not mean subtract. It means -12. It's a location. This second negative sign is an operator. Now it says subtract, take away from. So it's not that mathematically they're going to behave differently, just like in my head to make sure I understand what I'm doing. So I like to keep the 2 separate. And then I say, well, I need my initial position. My initial position is +3. So I look at these and I go, -12 minus +3 is like -12 minus 3, which is what? -15. So math is just the math again, but almost finished. I'm missing one thing. What am I missing? Units. I give you 3 shots, because I know sometimes people they'll get like a bit anxious and they'll kind of miss some units out because they're like over-focusing on the numbers. So you miss it one time, I don't mind. You miss it a second time, I don't mind. Miss it a third time, it's not that I don't mind, it's that there's no consequence. I'll write on your paper, hey, units, Third time, I'll write on your paper. Fourth time, you start losing points. Because it's not a slip, it's a problem. It's something where you're not in the habit. And typically I'll find in any class there'll be maybe one or two people and they've never got in the habits of doing units. And I got to address that with you, so that's how I address it. In terms of my distance travelled, well, let's call that DT. Distance travelled is the sum of all the bits. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So I'm getting 29 meters. I hope I did that right. I think I did that right. It's going to be 7 plus 10 is 17. And then plus 12 is going to be 29. I don't put a plus sign on it. Because, and this is just me, again, reinforcing so I make fewer slips. It's not that putting a plus sign on it would be wrong. It's that I'm trying to train myself more and more. If it's a positive vector, I'd call it plus something. If it's a negative vector, I'll call it negative something. If it's a scalar, I'll just call it the something. So if this was positive 12, I put down positive 12. If this was negative 12 for the vector, I put down negative 12. If it's just 12 for a scalar, I'll put down 12. Because there's not a negative scalar. There's only positive. So I don't need to distinguish scalars like that. So it's just, again, it's just like, oh, that's a scalar. It's got no sign in front of it. Yeah, that's a scalar. I'm not perfect with it, but that's what I try and do. Okay. Cool. So that pattern, you draw a diagram, well, you listen, you read the words, you draw a diagram, and then you interrogate the diagram. I'm not looking at the blue writing when I'm doing the math. I'm looking at the diagram. And when I come to check this, when I've finished, I will basically look at my answer, look at my diagram and check, look at my answer, look at my diagram and check. And then I'll do 7, where's that used? I'll be checking my diagram. So I work backwards through it. Because if I make the same way through things, if I make a slip going forwards and I go forwards a second time, I may well make that slip a second time. So I try and pull the question apart without going through at the same time. I also will work backwards through the test rather than forwards through the test. Because if I have a question on velocity versus time for question 3, and the question 4 is on position or displacement versus time, sometimes people will have velocity versus time from question 3 when they look at question 4, and they'll answer it as if it's a velocity versus time. Whereas if they work their way backwards, then you didn't see the velocity versus time before you got to position versus time. You're more likely to catch something. So Britain has high-stakes exams at the end of the year. They don't have many exams like this. They have high-stakes exams at the end of the year. And you've got to get really good, kind of like double checking and triple checking your work. Average velocity versus speed. So basically now I have another symbol. This is average velocity. The bar typically we use for average. It's like balanced. It's like, oh, it's on average. On average, it's a velocity, whatever it is. And what this says is that my average velocity equals my displacement versus my time change. My displacement, of course, is my final position minus my initial position. And my time change was going to be my final time minus my initial time. We're going to compare that with speed. And speed is the distance traveled divided by the time taken. So again, two different issues. And again, I'm going to have a number line. We're only working in one dimension now. And we say an object starts at +9, so let's put our in the middle, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. That's +9. And then it moves 6 meters to the right in 4 seconds. Oh, so now I have time coming in. So here's a trick. put a little circle in, like it's a clock, and put 0, because that's where you begin. So 0 seconds. If you like, put 0s down, because that's where you begin. And it says, object moves 6 meters to the right, so that's going to be 1, 2, 3, 4, 5, 6. And now we're at plus 15. And how long did that take? That took 4 seconds. And let's put a little arrow in to show we went in that direction. The object is stationary for 5 seconds. Okay, well, let's just leave it where it is. But now the clock has ticked away to 9 seconds. The object then moves 3 meters to the left in 2 seconds. So now I'm going to go from 15 to 12. So I'm here, and this is plus 12. And now the clock says 11. So I started off at 9, and I went to 15. I sat there for a while, and then I went back to plus 12. And I'm not given that plus 12. It's basically, you know, it's a combination of these things, isn't it? It's the 9 plus the 5 gave me 15. Sorry, the 9 plus the 6 gives me 15, and then 3 meters to the left, so I get my 12. So it's not a, it's a sophisticated interpretation. It's not just taking numbers from the question and bunging them into an equation. This is not substitution. This is interpretation. And if you're not comfortable drawing diagrams, then this is going to be a lot harder than the math would lead you to believe. I don't care about the fact that this is all over to one side. It's a calculation. It's just the way it worked out. I don't care about that. It's as long as it's clear to me what I did, I'm happy with it. I come along and I say, well, what is my average velocity? My average velocity is equal to my displacement over my duration, if you like, my time interval, which equals my final address minus my initial address over my final time minus my initial time. That should be T initial, that should be T final. So now I am looking at my diagram. I'm not looking at the blue words, I'm only looking at my diagram. And I go, well, what is my final address? My final address is plus 12. And what is my initial address? Well, my initial address is plus 9. And what is my final time? Oh, my final time is 11. And what is my initial time? My initial time in this case is 0. So V average is going to equal, what was it? 12 minus 9 is plus 3 over 11. So that would be plus 0.22, 77, 2277, I guess. So that would be plus 0.327, we'll leave it at that, 27 meters per second. And notice I'm breaking my significant figure rules all over the place. You do the significant figures in that question in the significant figures section. Say, using appropriate significant figures. You're going to use it then. Rest of the time, just give me a couple of decimal places, 1 or 2 decimal places, so I can just look and say, oh yeah, that's the right answer. The alternative that I have to do is I have to give you all the numbers as 3 significant figures. And then if I put down 5 kilograms, 5.000, it's easy to misread that as 500, and then the problem's wrong because of misreading. So the trade-off that most teachers make is we'll just use 1 or 2 significant figures on the question, but want our answer to be run long enough so we can see what it should be. Now, here's a bit of interesting thing. I can represent that. There's my average velocity is that displacement over time. So from my diagram, actually, I could see even from my diagram that my displacement was plus 3 just by counting. You go, oh yeah, it starts off there, ends there, plus 1, plus 2, plus 3. I can do that from my diagram and get that that value is my displacement. If I look at my speed is equal to my distance travelled over the time taken, which equals, well, now let's have a look. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 over 11, which equals 0.99, 8 times 88, 2, 1, 8, something like that. I'm going to call that 0.82. I think that's fair enough, meters per second. Don't bother with a sign on it because it's always positive because it's a scalar. Yeah, not bad. It's practice. Warning. I don't have to start the journey off when the clock says 0. The clock doesn't say 0 now when we begin class. It said 11 o'clock when we began class. No one's really confused by that. You're going, oh man, what's going on? So not all journeys begin when the clock says 0. So I could turn around and say an object starts at 9 meters, plus 9 meters, when the clock says plus 7 seconds. And I go from there. And again, you'd have 9 in there, and you'd have other numbers in here, and that's where the final minus the initial comes in nicely. So don't just look at the final time you see up here and say, well, that's my time interval, because I might not have started you off at 0. I might have started you off, clock says minus 3 seconds before you begin, before the clock reaches 0. It all works. So again, this is like, sometimes people go, this is so easy, I don't need to even practice this. And then they make mistake after mistake after mistake. And why we're doing this? We're doing this to kind of train you in using numbers right, using symbols right, and the like. Third bit, acceleration versus pickup. So my acceleration, my average acceleration is my change in velocity over my change in time, which is my v final minus my v initial over my t final minus my t initial. And my average pickup. Now, most people would call that acceleration again, and I just want to have 2 different words. So, people talk about my car has a lot of pickup, meaning it accelerates really well. So I kind of latched on to pickup as the colloquial term. And average pickup is a scalar, and it only has magnitude, and it's change in speed over change in time. So again, we have to do a number line, so we do our number line now. An object has a velocity of that at that, and there's no position for it. I could give you a position for it, but I need not bother giving you a position for it. So in this case, I just didn't give you a position for it. I just said, this time you have a certain velocity. So what I tend to do there is I'll go, okay, there's no position. So I'm going to have my clock is still going to be plus 7. And my velocity is going to equal plus 5 meters per second. And then the object has a velocity of minus 17 at plus 25. So here we are at plus 25. And now I have minus 17 meters per second. My little arrow is just roughly pointing the direction I'm going to go in. And what's the acceleration? What's the average acceleration during this time interval? So the average acceleration, my average acceleration, is equal to my change in velocity over my change in time, which equals my v final minus v initial over my t final minus my t initial, which equal, and now I'm looking at my diagram, and I go minus 17 minus plus 5 over, and now I'm still looking at my diagram, and I'm saying 25 minus 7. 25 minus 7, yeah. So that is going to equal, minus 17 minus 5 is minus 22 over 25 minus 17 is going to be 18, I think that is. So that's going to equal, let's get down to simpler numbers, minus 11 over 9, which equals minus 1.2, let's leave it like that, 1.2 meters per second squared. Put in a box. then my pickup is equal to my change in speed over my change in time. And I think for this, actually, pickup is equal to, I just don't worry about the signs. So I have 17 minus 5 over difference in time would be 25 minus 7, which equals, what's that, 12 over 18, which is 0.66 meters per second squared. That's, again, that's a scale. So compare and contrast, compare and contrast, compare and contrast. I'm, you know, frankly more interested in the displacement, but there's going to be like a whole bunch of weeks when I'm going to be asking you about displacement. So don't write off the others by saying, yeah, it'll never come up. They could either combination could come up. Maybe ask you displacement or distance traveled, etc. So don't write one off versus the other. Questions on this? Okay. At t equals 3 seconds, the car is at 16 meters per second. At t equals 9 seconds, it's at plus 6 meters. At t equals 12 seconds, it is at minus 8 meters. What is the displacement as a result of the journey, and what is the distance traveled? So I'll give you the displacement first and the displacement second, and the distance traveled second. Can you have a go at that for me, please? I'm going to just pause this. So let's have a look at this. So this is, let's just do this together. So this is a number line. At t equals 3 seconds, it's at minus 16. So minus 16, and this is at 3 seconds. And at t equals 9 seconds, it's at plus 6. So here's plus 6, and this is at 9 seconds. And at t equals 12 seconds, it's at minus 8. So minus 8, and this is at 12 seconds. And it says, what is displacement? So I say, well, delta x is equal to x final minus x initial, which equals, now I'm looking at my diagram. I went from, I didn't do my arrows, which is bad form on my part. I went from there to there, and then went there to there. So my x final would be minus 8, and my x initial would be minus 16. So this would be equal to minus 8 minus minus 16 is plus 8 meters. So there's my first answer. And then for my distance traveled, then that would be, let's have a look. I started off at minus 16. So there's 16 plus 6 makes 22. Minus 6, plus another 6 going in the negative direction makes 28. Plus another 8 makes 36. So this is going to be 36 meters. So if I look at that, I can see it's plus 8 and 36. And so if you got minus 8 and 36, which is B, just check your signs. Did you put your things in parentheses? Is it number line confusion? Is it writing confusion? Just see how it goes. So not bad. I didn't use the time. Yeah, that's red herring. That's just there. I want to see if you're going to use it. You don't need it. You know, you'll never get, or rarely will you get, just the numbers you need with. So you can just say, oh, like it's going to be that plus that equals that. There's always going to be some visualization involved. Cool. Can you ever go at that one for me, please? So let's have a look at this. Let's have a look at t equals 5 seconds. A car is at minus 16, so we have here minus 16, and it's at t equals 5 seconds. At t equals 9 seconds, it's located 6 meters to the right of the starting point. So this would be minus 10, and that would be 9 seconds. It's 6 meters to the right of the starting point, so I went like that. And then after another 2 seconds, it's at minus 12. Oh my word, minus 12, okay. So now we're back here. And this is after another 2 seconds, so that's going to be 11. So let me just check that again. I started off at 5, and I was at minus 16. And then at 9, not a change of time, but an actual time on the clock at t equals 9 seconds, I was at 6 meters to the right, so that means minus 10. After another 2 seconds, so now it is a time difference, it's another 2 seconds, so 9 goes to 11, and I'm at an address, and the address is minus 12. So what is the average velocity? Velocity is equal to my displacement divided by my time, which equals my final position minus my initial position over my final time minus my initial time. And I'm looking at my diagram, and I'm going, my final position is minus 12, and my initial position is minus 16, and my final time is 11, and my initial time equaled 5. So if I did that right, minus 12 minus 16 is minus 12 plus 16, which is plus 4, over 11 minus 5 is 6, so that's going to be 0 plus 0.66 meters per second. Did I do that right? Did I do that right? Yeah, see on that. So again, you know, if you use your read your words, you do your diagram, you do your math. Question or comment?
If something like this is on the test, because I got the right answer, I did it wrong. So.
Oh, I look at your work.
No.
I look at your work. Yeah, sorry. Sometimes I get people they make 2 mistakes, and they go, but I got the right answer. I go, you know, hey, it's the number's just the number. It's the method that counts. So yeah, sorry. But yeah. This next one, a car starts from rest after 4 seconds. It has a velocity of minus 12. What is its average acceleration? I'll leave you to play with that. I think the answer to that is on the homework help section, so I'll leave you to look at that one, but it follows the same principle. Let's have a look. I am going to pause there, so I'm going to stop this tape.